My name is Claudio Canizares. I'm the Executive Director of the Waterloo Institute for Sustainable Energy, who is hosting this lecture. So before I start with the introductions, let me read the territorial acknowledgement as required by University of Waterloo. University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations that includes 6 miles of each side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relations. Thank you, everybody, for attending. Thank you particularly to Abhishek, who has agreed to deliver this lecture. His team focuses on quantifying and managing climatic and environmental loads on buildings to design climate resilient and sustainable structures integrated with nature-based solutions in Canada. Dr. Gore's work has contributed to the 2025 National Building Code of Canada. He also co-led the Weather Data and Policy Task Forces of the International Energy Agency's Buildings and Communities Program, Advancing Climate Resilient Cooling in Buildings. He earned his PhD in Civil and Environmental Engineering from Western University in Canada. Thank you, Abhishek, for agreeing to deliver this lecture. Welcome virtually to Waterloo. Look forward to your presentation. So you might want to share your slides now. You should be able to do that.
Okay. Thank you, Claudio, for the introduction and for the invitation. Thank you, as well as Armugan, who invited me and to present the work we are doing and how perhaps it can stimulate some interesting ideas for collaborations in the future. So my work here, I'll start by introducing myself. Claudia has already done that a little bit, but I lead the Building and Climate Interface team here at National Research Council, and our work is focused on managing and quantifying climatic and environmental loads on buildings. In this presentation, I'll try and focus it on some of our initiatives to develop climatic data to support the design of climate resilient, low carbon buildings. So as perhaps all of you know, because you have, you're all building practitioners, we know that buildings are expected to be structurally secure against the climatic loads, as well as at the same time deliver high levels of performance in terms of energy use or thermal performance and so on. Yeah, and to design the buildings, we need reliable information on climate over the design life of the building. So we need information on the long-term climatic data. We all recognize that buildings are impacted by several climate-related factors, such as climatic extremes, but buildings also are able to shape the climate around them, which is perhaps a little bit less recognized and appreciated. For conducting building simulations, which are used to design buildings for their efficient performance, we need a range of climatic inputs, ranging from temperature, humidity, solar radiation. For agrothermal simulations, we also need moisture-related parameters, usually in high temporal frequency. As well as another consideration is that they should reflect the climatic conditions next to the buildings. And usually there's lack of data just next to the buildings or at the urban locations, because most of the climatic data is usually available at the airports and so on. Yeah, and so like in this regard, there's a need for urban climatic data to be able to design buildings that are structurally secure as well as high performance. We all know that climate change is impacting the long-term climate settings of Canada, and how and that consequently is expected to affect the design of buildings. In this figure on the right, you can see the expected change or the historical actually the change in precipitation that have been recorded over the last 70 years since the 1950s. And you could see that the places in the north usually have experienced a much quite high percent increase in precipitation. But in general, in Canada, almost all of Canada has experienced an increase in total precipitation over the last 50, 70 years. And it's the same story when we look at temperatures, temperature extremes, and so on. Another point to highlight is that urban areas are different in terms of their microclimate because of the presence of buildings, their 3D structure, the amount of emissions made in the urban canopy. So the way urban areas are getting affected by the effects of climate change are very different from non-urban areas. They are also associated with a much higher risk because of the presence of population and economic development in the urban areas, the presence of buildings, and so on. And these risks are growing with the expansion of urban areas, with the increase in urban population, and so on. So when we start looking at long-term climatic exposure of buildings, it's important to consider the long-term effects from changing climate, but also the effects of expanding urban areas, growing population, increasing anthropogenic emissions in the urban areas. And therefore, the focus of our research group is on quantifying and managing climatic and environmental loads in an effort to develop climate resilient low carbon buildings and communities in Canada. So as discussed, there are several different factors. When we start looking at the climatic and environmental exposure of buildings, they can range from factors like extreme events, or in general, the climatic setting of that particular urban area. In terms of environmental factors, say the presence of urban trees, water features, and some anthropogenic or anthropogenic factors as well. Say the use of building materials in buildings, the presence of urban canyon, urban canopy, the 3D structure of the buildings. So all these different factors, they interact and influence the kind of exposure, climatic and environmental exposure of buildings. And there's an opportunity to understand those factors, because if we do, we are able to better manage them, which in turn allows us to develop more sustainable buildings. In this regard, our work is currently focused on 5 different directions. I'll start with the first key area of our research, that is on developing climate data and loads related information for the design of buildings. In this regard, we have developed hourly climatic databases to support the design of buildings. We have developed projected future building simulation climatic data sets for more than 500 different locations in Canada. And again, as I was mentioning, these are climate files which contain all the parameters in hourly time steps that one needs to conduct building simulations. We have made sure or made an effort to make available these data sets so that they are convenient in terms of format required for building simulations. The data is available, for example, in the EPW format, for quick ingestion into popular building simulation softwares. And all of this data is available for public access from NRC libraries. The data set is recognized in Canada by Environment Canada, has been discussed as one of the prominent data sets to assess the effects of climatic change on building performance. The methodology we have used has also been adopted by the International Energy Agency to design sustainable cooling solutions in cities, and has been published in peer-reviewed journals. The data sets have been used internally across NRC. So just to give you a sense of how the data have informed different types of building analysis, it has been used to, for example, conduct hydrothermal simulations and design moisture resilient buildings, also to conduct whole building simulations and design energy efficient buildings, which are also resilient to overheating risk. The data sets have also been used in the context of durability, enhancing durability of building components, then also to design climate resilient roofing systems integrated with nature-based solutions, and are the key databases which are informing the climate RCI tool from NRC. This data also informs the climate resilient design of pavements, as well as analysis that is being conducted to model the wildfire hazard around the Canadian cities. So a lot of different teams have been using the data sets we have produced to design buildings that are resilient to different types of climate risks, as well as to optimize their performance for many different aspects. Beyond NRC, the data, as I mentioned, has been the methodology has been used by the International Energy Agency to develop climatic data for building performance simulations for 15 cities worldwide. A number of cities in Canada and US, as well as globally, have used the methodologies and data sets we have produced. And so the data sets and methods we are developing are informing and helping develop resilient, sustainable buildings around the globe. In addition to this hourly climatic databases, which are being used to inform the design of high-performance building, we are also working to derive buildings design climatic indices. So as you know, in the National Building Code of Canada, we do have a table which basically lists for around more than 800 locations. Yes, more than 600 locations, the different building design parameters. And so in the past, we have worked to update this information in two different regards. First, to use more recent climatic observations to update this table, but also to incorporate the effects of changing climate in the climatic design information. So basically, to do that, all the projected changes in different buildings related design parameters were analyzed for all the 680 reference locations in the National Building Code of Canada. Essentially, for each of these design parameters, the range of changes among them are listed here, but they were analyzed for each individual location. And then for locations where there was an increase in the amount of loads projected in the future, a recommendation was made to increase the design parameters by that amount. So this exercise was done for over the last 4 or 5 years and is expected to inform the 2025 National Building Code. Just to give an example, how one of the parameters, moisture index, was calculated. Basically, the climatic projections were taken from the Canadian Regional Climate Model, and a process was adopted to basically following the National Building Code as to how the moisture index needs to be calculated. That process was followed with the projections made by the Canadian Regional Climate Model, and for all the 680 locations shown here, we calculated the amount of projected change over the next 50 years. And those are basically shown here. Among the 680 locations, we found that in areas which are near the coast, an increase in moisture index can be expected. Whereas in the prairies areas, in the northern regions, a decrease in moisture index was predicted. How this translates into the building's design was also analyzed. In the building code, again, there are some guidance provided as to which locations need to have a capillary break in the design of wall assemblies. Basically, locations where one of these two conditions are met, one needs to incorporate an additional capillary break in the design of wall assemblies to ensure the walls are resilient to moisture ingress. And so an analysis was done as to which additional locations would require that kind of additional protection measure. And we found that 82 additional locations would require a necessary capillary break. So this kind of analysis was done to support the recommendations made for the update of the building design indices. Moving over to the next key area of our work, which is related to overheating and thermal comfort. So as we discussed, as I briefly discussed in the beginning of this presentation, that urban climate is different from the climate in the non-urban areas. It is definitely influenced by the global factors, but also shaped by the regional factors, by the urban built form emissions, as well as the presence of trees nearby, or the presence of nature-based solutions in general. We do not have a lot of information in terms of observations or the models to study urban climate. And so our focus has been to develop such databases for urban areas in Canada. In this regard, we have taken two different approaches. One focusing on the urban climate measurements, where we use sensors to and place them strategically in different types of urban contexts to record urban parameters. This is also focus of much of our future work. But in addition to that, observational based studies, we are also conducting very high resolution urban climate modeling using models like weather research and forecasting, as well, and VMET, for example. So using these models, we are able to simulate the climate parameters next to the buildings or over a neighborhood or over the entire city, taking into consideration the distribution of trees, the presence of water bodies, the topography, the emissions made in the urban areas, and a lot of different factors that are not really captured if the modeling is done at a much coarser level, at a regional level, or if the analysis is done using, say, observations made at the airport locations, because those locations don't really capture what actually happens within the urban areas. So we are able to, so our focus has been to derive and consolidate information for urban areas, because most of the buildings are actually located in the urban areas. So we ought to use the data sets which are suitable for their design. Just to give you an idea, like urban heat island effects, for example, in large cities, they can be as high as say, 10 degrees C. So if we are not able to capture those kind of effects, we are not able to simulate, say, effects on indoor overheating or effects on the energy used for cooling the buildings and so on. So everything would be quite under predicted or under simulated if we ignore those effects. This is just an example of the kind of work we have done for the city of Montreal, for example, where we used different matrices where we have developed, first of all, 30-year or long-term climate files, but then for simulations, because we ought to select a particular year for simulations. So for energy applications, for example, that is usually a typical meteorological year. But for energy, for overheating or extreme heat analysis, there are some other indices used which capture those extreme heat profiles. So we have used the methods available from the literature, as well as developed what we feel a more representative method to select extreme heat reference years, and which we are using to do simulations of indoor environment in buildings in those heat spell events or heat spell years, extreme years. So again, such data of extreme heat reference years has also been developed for all these different locations to support the analysis of overheating in indoor overheating in buildings, as well as at the same time sort of also evaluate, say, the effects on energy or the cooling demand in buildings and so on. So these data sets have been made available and are being used by us as well as across NRC and Canada to make such evaluations. In overheating, we have also been publishing several guidelines to manage overheating risk in buildings, while also ensuring that buildings perform in an energy efficient way. As well, guidelines in Canada as well as internationally are being developed in this regard. Another key focus area of our work is on nature-based solutions. In this regard, we are able to use models like NVMet, for example, which are able to take into consideration the different greenery aspects integrated onto building facades, or the presence of street trees, while modeling the climate next to the buildings, and then also coupling it with building models to see how they in turn influence indoor environment within the buildings, as well as the energy consumption and so on. So we are able to simulate these aspects quite reliably with the use of the models, both at the building or street level, but also then we are able to use little bit coarser models, but also goes to a city level analysis using models like WRF, and evaluate their effects on climate at the city level or at the street level or neighborhood level. So some of the results from previous work which we have completed and published, where we used WRF model to see how changing albedos in urban areas and in different cities, or changing the percentage of greenery in different cities, can translate into changes in urban climate. And then, of course, how that translates into how that affects the building performance is another aspect that for which this information is used. So yes, we are able to look into all these aspects and see their effect on the climate next to the buildings, as well as indoor environment inside the buildings. Just an example of another study that we conducted on the effectiveness of street trees in reducing the risk of overheating. Basically, we looked into a neighborhood a residential neighborhood in the city of London, where the baseline tree cover was around 6%. And we created another scenario of fully grown trees, where the tree cover was about 9%, and then also generated some more scenarios by increasing the amount of tree cover to 30%, 40%, and basically evaluated how that cools down the neighborhood in an extreme heat event. So these are some of the analysis that we are able to do. And of course, all this information is then coupled with building models to evaluate the effect on energy efficiency or energy consumption for cooling, or like temperature profiling different parts of the building and so on. Our current efforts in this direction are basically on looking into aspects that need to be considered while we are integrating nature-based solutions onto the buildings or neighborhood. So what aspects we ought to take into consideration from the municipal point of view or from the building code point of view when we add greenery. So that's an area on which we are collaborating with municipalities as well as building code experts. Another area of our current work is on evaluating the costs and benefits of doing so. Especially so in benefits, we are focusing on the benefits in terms of health improvement from the reduction of overheating, of course, the amount of energy saved during summers, and so on. So essentially developing methodologies to quantify the costs and benefits. It could be a good, an important decision support tool for practitioners. We're also working on developing wildfire resilient buildings. Again, like in Canada, we know that there have been a number of extreme wildfires which have caused enormous amount of socioeconomic damage. It's one of the most concerning natural disasters, which is expected to get even worse with global warming. So to tackle the gap which was existing in terms of guidance to design buildings resilient to wildfires, over the last 5 years, NRC worked to develop the first national guide for wildland-urban interface fires. Basically, in this guide, it is enlisted, or it is described how to calculate wildfire hazard around a building? Like what factors? Is it governed by which models could be used, and so on? And then how to categorize the amount of wildfire hazard into several different categories. Secondly, of course, the amount of hazard has to translate onto the buildings, and buildings which are more exposed to such hazard. Say, for example, if they have a tree nearby, which a fuel type which can be burned, or if there is dry grass around the building, or if it is located upslope. So these factors, they influence the amount of exposure that a particular building can have to wildfires. And in the guide, it is mentioned how to calculate such exposure elements for each individual building. Thirdly, the level of property level mitigation done by homeowners also influences a lot on the vulnerability of buildings to wildfires. These three factors are combined together to provide guidance on how to design buildings so that they can remain resilient to the wildfires. Our current efforts are focused on obtaining the level of hazard, for example, in different parts of Canada. In this regard, Natural Resources, we are collaborating with Natural Resources Canada to obtain hazard values, for example, in all the National Building Code reference locations. And then also look in addition to that, the effects of changing climate. So the overall goal for this hazard assessment work is to obtain a value of hazard for different locations in Canada and categorize them in low, medium, high kind of hazard categories as defined in the Wildland Urban Interface Guide. For exposure assessment, we have been looking at using the satellite imagery, basically, and then analyzing those imageries along with the use of AI to derive the presence of trees around the buildings within the different exposure zones, the presence as well as the type of fuel, whether they can be burnt or not. So these kind of use of satellite imagery is being evaluated and implemented in certain communities. Of course, combining these different factors, we are reaching to the kind of construction class per se in the guide, which needs to be adopted to design the buildings. We're also looking at the current level of build of the buildings and whether it meets those criteria. If it doesn't, then if we do upgrade those buildings, how much it will cost, and in the long run, how much will be the benefits of making those upgrades. These are some of our current areas of work in this direction. And finally, recently we started some work on urban planning. As we discussed, the cities will continue to expand to cater to growing population. And if we are able to influence the city growth, taking into consideration, making sure that they are able to adapt, that cities are able to adapt to climate better, or are able to less emit the greenhouse gases and are able to achieve that cost effectively, then it will lead to a sustainable urban environment. So we have recently started a project on developing future building stock projections for select Canadian cities. And here, some of our efforts are to explore what can be done to optimize city growth in terms of these three different criteria, in terms of reducing climate-related risks. So, for example, risks of overheating. It can be achieving energy efficiency, for example, ensuring that the greenhouse gases emitted are reduced, and they can come from, say, buildings, from all the building energy uses, but also, say, the emissions made by the transportation sector. So we do plan to look at all these different aspects to see, can we minimize the amount of emissions made by these scenarios. And then, of course, in the long run, how cost effective that transformation can be. So these are can be optimized for these three different aspects to guide the future expansion of cities. We are also engaging with municipalities in this regard to see how such projections are currently being made, and then, like, can we do anything better in this regard? So yeah, this is still in an initial sort of stage of the work, but definitely an area that we are looking to work towards. Okay, in closing, our the goal of our work, which is to effectively manage the climatic and environmental loads around buildings. We are working towards that in 5 different directions. We are developing databases of climate data and loads to design buildings that are resilient as well as high performing. Overheating, extreme heat, and developing heat resilient buildings is again a major focus area for work, and we are supporting the building code updates in this direction as well from a lot of research that we are doing in this direction. Then we have actively participated in developing the Canada's first guide for wildland urban interface files. And at this time, we are our focus is to develop tools to support its implementation and adoption by communities. In fact, we are also committed to investigating the effectiveness of nature-based solutions in reducing climate risks, in developing guidelines as to how nature-based solutions should be integrated onto communities and buildings, keeping in mind different considerations from municipalities and building codes. And finally, we're trying to put together everything at one place to see if we can use all this information to guide to do a more effective urban planning, which is sustainable, climate resilient, and cost effective. We are also, like, we always are looking to collaborate with universities, with others, to be able to learn new technologies and to take feedback and make products and data sets which are useful for others. So if you see a possibility to collaborate, please feel free to reach out. Thanks for your attention, and this is my email. Very happy to, and again, thank you all for being here, and I'll be very happy if any of you have any questions. I'll do my best to answer.
Thanks, Abhishek. Thanks for a very interesting presentation. I have a lot of questions, but I think we'll parse them down and also give the opportunity for the audience to ask some questions. First of all, apologies again for the disruption of the start of the lecture. It will be, as Sarmugan posted on the website, apologies to everybody, and we'll make sure that this doesn't happen again. I guess we have been too trusting. So for the future, we'll be more careful. Now, in my question, I have a couple of questions to start with. We have our self-developed models like the ones you have described from the perspective of electricity demand. That was our main focus, figure out the electricity demand. But we had to develop building models and detailed thermal models, etc., appliance models, etc. Now, these are complex models. I mean, they take a lot of effort. So I was wondering, you have much more complex models than the one we have developed. So my question is, how complex these models are? Are they developed by yourselves for a particular type of software? And I think you already addressed this. And have they been validated with measurements?
Right. So, like in terms of like developing models, like for modeling, say, like all these climatic, environmental feedback, interactions, and so on. Like we haven't developed it from the scratch. The models like WRF, for example, they exist in the open science sort of framework, and definitely we have tuned the models for our like case studies. So, for example, if you are studying a particular city, we force them with the background conditions that are relevant for that particular city in terms of the setting of climatic parameters. Similarly, the amount, like the kind of buildings and their distribution across the city and so on, those things are sort of used as input. So there and some parameters need to be calibrated. So those kind of settings have been calibrated in the models. The models are usually quite computationally expensive, so we usually run them on clusters. Of course, depending on the amount of computational expense required, we have used different types of clusters as well. In terms of validating the data, we have primarily used measurements from, say, Environment Canada, and usually they don't capture, like as I was saying, a lot of the urban effects. So that way, the kind of validation that is done doesn't really capture much of the urban effects, but and that's why we have also measured some in-house data and validated the models to see how effectively they are able to capture those effects. We have also used some satellite data to see if the spatial patterns modeled by these models they are actually being accurately captured or sufficiently accurately captured by the models or not. I don't know if that answers the questions, but if I missed anything,
yeah, I think that gave me a good idea. Yeah, but from my experience, for our experience, our group experience in modeling buildings is quite challenging, and the parameters can make a big difference. So figuring out these parameters is a challenge. We have validated some of them with measurements, but it's always a major effort. And I guess we're building an existing software, which is, I guess, was part of my question. Thanks for that. Now I have a couple of questions here online. The first one about geothermal. Do you factor those issues in your building calculations, your models? Like, for example, ground source heat pumps or? you're
very
talking about it,
recently.
you just focus on the building itself, not as much as the appliances or.
So usually like how we have worked here is like in terms of developing data, we have developed data sets that allow for any kind of geothermal evaluation, technology evaluation. So in that regard, we have also worked with say Concordia University, where like one of the researchers, they were looking at like some solutions related to geothermal, and they required like surface temperatures up to I think like a few hundred centimeters below the ground level. So we are able to model those aspects and provide information that is useful for such analysis. Even within NRC, there are a number of teams who look at different aspects of buildings design. So like our work has been mostly to collaborate with them, be it geothermal solutions, and develop climate-related products, which are useful for that kind of work.
Thank you for that. There's another question here. It says, well, 3 questions in fact. What is the scope of the cost-benefit analysis you are considering?
Yeah, in terms of like costs, there has been a lot of focus on quantifying the costs associated with the total life cycle of all the materials being used in the building. So that has been on the cost side a major factor. In terms of benefits, a lot of our focus has been on health related benefits, like if a reduction of climate related risks, how they translate into health benefits and consequently monetary benefits. But of course, and another direction that we are going is also, of course, in terms of savings in operational energy demand. So these are 2 factors that we have looked at till now. But of course, there are many other factors which.
Second question was related to health impacts and says whether you consider extreme heat and wildfires in your studies. Directly related to health impacts.
Yes, so like in terms of extreme heat, we have developed some physiological models as well to see how different temperature ranges influence different types of demographics. We also made recommendations for indoor temperature thresholds. I think very recently there was a recommendation made to maintain at least 26 degrees as indoor temperature in Canadian like homes. That I think that these sort of guidelines were based on a lot of physiological studies done within our group to identify a suitable thermal sort of range to ensure there are no health risks to different types of populations.
And okay, and the last question is regarding indoor air quality, whether that was
right. Right. There's a so wildfires. Like my work has been mostly on these, ensuring that the structural component of it remains intact and following the guidelines for buildings design. But there's a section like the whole group on fire safety at NRC, and some people working there are working on the propagation of wildfire smoke from outdoors and then interaction to indoors, effects on air quality and so on. So yeah, I mean, happy to connect. There are definitely dedicated groups here at NRC, both on fire safety as well as indoor air quality, and they are usually looking at those aspects in a much deeper way.
Okay, thank you. Rebecca, you want to follow any of these questions, follow up?
Thanks. No, I just wanted to say, yes, I know that your folks under the Construction Research Center are working on a lot of this stuff in a very interesting way. And our group is really focused on, you mentioned cost benefit analysis. And so we try to estimate, health risk reductions from indoor air exposures and, for heat and air pollution and wildfires. So we'd be really excited to connect on some of those aspects. You're working on many different difficult things, so we'd love to help extend. Yeah.
No, it's great to know. In fact, so this is a relatively newer sort of group created focusing on this. We used to be slightly differently organized, but I think in the past a year or so, we have been organized differently to focus on these areas. But it's good to know that your group is sort of working on these, and I will be very happy to look at some of your work as well, because cost benefit analysis, urban planning are areas that we are sort of starting in the group. Definitely, we want to grow that area of work moving forward.
Well, thank you for that. I guess Rebecca will be following up with you directly. Any further questions? I don't see any other questions on the chat. No hands raised. Okay, so thank you very much again for your presentation, Abhishek. Very quite interesting. In fact, it's somewhat relevant to what we do in microgrids and electricity demand, especially from the sense of thermal and electrical systems, which are becoming quite relevant. So thank you very much for that. I appreciate your time and effort.
Thank you for the invitation. Great meeting you all. Look forward to hopefully working with some of you in future. Thank you.
Thank you, Abhishek.
Thank you so much.
Bye now.